So let's continue our study of center of mass. Our study of center of mass is going to be focused on two different categories. One, finding the center of mass of some system of discrete particles. You've seen an example of that. Maybe you found the center of mass of the Earth-Moon system. We say that the location of the center of mass along the x-axis for any number of objects can be found by taking the mass of object 1 times its position plus the mass of object 2 times its position, so on and so forth, all divided by the total mass of the system of objects. Another way of stating that, the location of the center of mass is equal to the sum of the product of mass and position, all divided by total mass. When it comes to a rigid body, we use nearly the same formula. We just turn it into the language of calculus and say the location of the center of mass is equal to 1 over the total mass multiplied by the integral of x dm. And I'll give you an example of what we mean by that by finding the center of mass of a rigid body in the shape of a triangle. If we look at this the right way, we can think of the triangle as being a collection of discrete particles. So let's start out by making a coordinate system, and we'll put this triangle on the xy axis with one of its vertices located at the origin. Now I'm going to guess the center of mass of a triangle is located maybe somewhere around that spot. Here's what I mean by turning this into a collection of discrete particles. I can imagine slicing the triangle up into a bunch of thin little slices. Now the total mass of this triangle, we'll say, just has a mass of capital M, and it also has a total area we'll call capital A, and we know that the area is 1/2 base times height. So the triangle has a distance along the x-axis of B that brings us to the end of its base, and it's got a height along the y-axis of H. Well, each of these little slices, I'm going to make it so thin that the little bit of width each slice takes up, that we label as dx, approaches 0. So let me draw one of these slices over here, and imagine how much of the total mass of this triangle does that take up? Well, it just takes up a small fraction of the total mass, so we'll call that dm. So that's the dm we're referring to in this equation. So what's the x that we're referring to? Well, for any given dm that we identify, it sits at some position away from the origin in our diagram that we would label as x. So each unique dm, here's another dm right here, it's also sitting at a distance from the origin that we could label as x. So this is what we're up to. We're trying to add up, we're trying to integrate the product of each little bit of mass that represents a slice of the triangle multiplied by its particular position. So let's just see if we can use this equation to verify that our guess is correct for the location of the center of mass. So let's restate the equation we're working with. The location of the center of mass, at least along the x-axis, is equal to 1 over the total mass times the integral of x dm. Now this is a bit tricky because we have two different variables, m and x, but we want to turn this into calculus of a single variable. So we need to find a way to describe m in terms of x, and that's probably the trickiest part of this whole solution. But think of it this way. Mass per unit area should be just some singular constant value for this triangle. In other words, if I take the whole triangle and I find that ratio by taking its total mass divided by its total area, keep in mind, as we already said earlier, the total area is 1/2 base times height. Okay, that ratio of mass over area should be the exact same numerical value I get if I were just take the ratio of mass to area for any single slice. So let's pull this slice out of here. Well, we know its width. Its width is dx, and we know its height. Its height is some distance up the y-axis. So if I divide the mass of the slice, which is dm, by its area, which I guess we'll just call dA, and then we know what dA is. Since this little slice forms a rectangle, dA would be nothing more than y times dx. So that ratio of mass to area and that ratio of mass to area must be equivalent in value. Think of it sort of like a density, but instead of units of kilograms per cubic meter, we're finding the density in terms of area. It would be some number of kilograms per square meter. Okay, so back to the task at hand, finding the location of the center of mass. 1 over the total mass times the integral of x. Now, instead of saying dm, I can say what dm is equal to. I can make a substitution. If dm over dA, the ratio of kilograms per square meter of the slice, is equal to the ratio of capital M over capital A, the total number of kilograms per square meter for the whole triangle, then that means dm is equal to M over A times dA. So that's the substitution I'll make. M over A times dA. So it's still not quite calculus of a single variable, but it will be as soon as I substitute for dA. So what am I going to substitute in place for dA? Yeah, you probably already see it. We're going to substitute y dx in place of dA. So now we get the location of the center of mass is 1 over capital M. Pull the capital M over capital A out of the integral, and we're left with the integral of x. And I'm not going to say dA, I'm going to say y dx. We're still stuck because we've now introduced another second variable y, but we can get y in terms of x. That's really easy. See, we've got a right triangle, and we've identified a small fraction of the total mass of that as dm, and that dm sits at a distance x away from the origin, and that particular slice of the triangle has a height of y. So we can see there's an angle right here, and I think you agree that the tangent of that angle is y over x, but the tangent of that angle is also the height over the base. So y over x is equal to h over b. So we can make the substitution y is equal to h over b times x. So we'll make that substitution back into our equation. Now that gives us the location of center of mass is 1 over m times m over a times the integral of x times h over b times x dx. So let's cancel a few terms here. The capital M's cancel away. I can substitute in place of a 1/2 base times height. When I do that, that h cancels with that h. So let's simplify a little bit, see what we're left with. xcm is equal to, they've got a 1/2 in a denominator, so let's just make that like a 2 in the numerator. So we've got 2 over b, and then we've got all of these terms from that part of the integral taken care of. Let's pull this b out of the integral, so there's a 1 over b, and then within the integral we're left with x squared dx. I think we've skipped a step. We didn't bother yet to consider our limits of integration. If we scroll back, we can see in our picture what the limits of integration are. Our very first slice is way back here, where x equals 0, and the very last slice we have to account for. The last dm sits at a value of x equals b. So there's our limits of integration. We're integrating from 0 to b. So now we've got the location of the center of mass is 2 over b squared. And then the integral of x squared dx is 1/3 x cubed. And we're going to evaluate that from 0 to b. And that's just going to give us 1/3 b cubed. So I think we've got the location along the x-axis as 2 over b squared times 1/3 b cubed. And that simplifies to 2/3 b. So what does that mean? Well, we have the triangle on our xy axis, and we guessed that the center of mass is somewhere around here, and that looks about right. The distance down the x-axis, it looks reasonable to say that's about 2/3 the base of the triangle. So now the question is, how far up the y-axis is that center of mass located? Well, we'll treat that as a separate calculation. So here's the approach we can take. Instead of figuring out how far up from the base the center of mass is located along the y-axis, we'll figure it out this way. How far down from this corner is the center of mass located? So we can do that just by rotating and rearranging the picture. So if we draw our xy axis once again, and imagine taking and rotating this over to here and flipping it. Now we've got the triangle sitting this way, and this time what used to be the base is now sitting along the y-axis, and we've got h sitting along the x-axis. So we actually don't really need to, we could have done it a longer way and sliced it all up into slices along the y-axis and essentially done the same calculation we did before. But I think you can see if we do it this way, now that we're integrating along the x-axis once again, we know exactly where this point is going to be located. We've already determined this. That would be at a distance now of 2/3 of h. But remember, that's how far down from this corner. The corner in this picture right here is the same as this corner. So if this is 2/3 of h, then this must be 1/3 h. So we figured it out. For any right triangle, the location of its center of mass, if we place it on the xy axis, is located at the coordinates 2/3 b, 1/3 h.